So the next function that we want to implement is post-order traversal of binary tree. So let's go to our header file and let's add a signature. Post-order traversal, bt node and root. Now we want to provide the implementation of this function. So let's go to our traversals file and add the signature in the end. That is what our post order will look like. So we have pre-order here and we have level order. So in post order also we are going to use a stack, and because this is the iterative version, so we will need a stack to store our nodes. So let's first discuss the idea of post order traversal. Let's say this is our tree and we want to print post order, which means 2 will be printed after its left subtree is printed completely and right subtree is printed completely. So what we will do with stack is we will first push 2 onto the stack, then we'll keep moving on to the left of it till we cover entire left subtree. So with that we'll make sure like 2 is not printed till entire left subtree is printed. So we keep moving down till we find node which does not have a left subtree. So once we reach down that node, after that what we want to do, we want to start popping out like we did in pre-order traversal. So we pop 4 out, but right now we are not sure whether we should be printing 4 or not. The reason behind that is we need to ask another question: is right subtree of 4 covered or not? Because when we are pushing items on stack, we are pushing all the left subtree of any node that we come across. But when we pop, that time we need to ask this question: is the right subtree of that node covered or not? So let's take example of 5. So when we pop 5 out of our stack, we want to know, is left subtree covered? That is implicitly covered, because when we initially follow the left subtree, we are keeping on pushing, like 5 we push and then we move to left. So we can rest assured like whatever is there on the stack, left subtree of that is already covered. But for right we are not sure. So we will use a strategy that when we are pushing an item on stack, before pushing 5, we will push its right subtree, its right child in fact. So before pushing 5, if we push 9 on the stack, so at the time when we pop 5, we can check with previous item that is there on the stack. If that is right child of 5, that means right is not yet covered. If 5 is not there on the stack, we can rest assured like right subtree of 5 is already covered. So this is the trick that we will use, pushing an element which is right child of 5. So with that, let's first start coding. So let me create a stack. Create stack. And so that we don't forget destroying it, let me add a destroy call also here. So let's run a loop so that we cover all the nodes in our tree. So first loop that we talked about, as we did in pre-order, so we want to push root onto stack. So give stack on which we want to push and then we give root. And after pushing root, we want to keep moving root equals root of left. This is the strategy we used in our pre-order. But here we said we want to do one thing. Before pushing root, we want to check if root has a right child, we'll push that first. So if root right is not null, that means root has a right child, so we should push that first. And then we should move to root. So with that, if we see with this logic, where will we go in our tree? So we come to 2. 2 has a right child. So initially our root will be pointing to 2. When we come to this loop, okay, let me make while root not equal to null, because we want to keep moving down till we find a node which is null. Yeah. So right now root right is not null because 2 has a right child which is 3. So we will come to this and we will be pushing our root. So let's push root's right, which is 3. So 3 is pushed onto the stack, and then we come here, then we push 2 itself, then we push root. So first we pushed right child of root and then root itself. Then we move root is equal to root left. So now root starts pointing to 1. That is root left. So when we come here, again there is a check. Root not equal to null, which is true. Root's right child not equal to null, so we push root right. Here 1 does not have a right child. So if 1 is root, root of right is null, so we don't go inside this if condition, and we come here and we end up pushing 1. So 1 is pushed here. After 1 is pushed, we do root is equal to root left. That means root comes here. Root start pointing to 5. After coming to 5, again we go up and we check the condition, which is true. We don't we come to this condition. If 5 has a right child, here this condition is true. 5 has a right child, which is 9. So we first push 9 and then we will push 5. So first 9 goes in, then 5. Then we again do root equals root left, which is we point to 4. Then we go up. 4 does not have a right child, so 4 will be pushed and root will start pointing to null. Root equals root left. So root is 4, root left is null. So we come out of this loop. So after we come out of this loop, 4 is there on top of the stack. So next operation that we want to do is we want to do root equals pop. Since root has become null from previous loop, so we are directly using root variable to pop item. So once we pop, now we have to make a decision. Can we print this value directly? So in post order, we cannot print a root if its left and right children are not covered. So first loop takes care of covering the left subtree, but right we are not sure. So here we cannot directly print root. For printing root, we'll have to make a decision based on is it right covered or not. So how will we check if it's right covered or not? We'll do a pop of previous item and we will check whether that item is right of root. If the item that is put on stack that was right child of root, that means right we haven't yet covered. So we'll extract the right and we will start traversing right. If right child is not the previous item, what we will do, we'll proceed, we'll print the current value and we'll start traversal again. So traversal again means we'll print the current value. That means we'll print 5 if left and right child are both covered, and we'll proceed by popping the previous value onto from the stack. So let's check the decision. So how do we check if previous item on stack is right child of root? That means we have to do one more pop. So let's declare one more variable, temp, and pop another item. After popping, we want to check if the item that we have popped is that right child of the root. If true, then we'll do some logic. Otherwise, if it is not the right child, then we know we have to print current item for sure. So root's data we can directly print. So now we come to this case. If previous item that is onto the stack that is actually right child of root, so what we want to do, next thing that we want to do is root equals root of right. We want this to proceed so that with right child of root we can do the same processing again. We can do the post order traversal of right subtree. Now if you notice, we have popped 2 items from the stack. So we need to push it back, because if we have seen like previous item was right child, then we should proceed with the right child, but root should be kept back into the stack, because we want to come back to print root. After we are done with the right subtree, we'll want to print the root as well. So 2 pops have happened here, 1 push should happen back. So before we move root to the right, we should push root back onto the stack. So that completes our if part. If this matches, then what we have done, we have essentially gone to the right subtree and we are traversing that, and we have pushed the root back. So next time when you pop this root, previous item will not be the right child of that, so we can rest assured we can go to the else part and we can print the data of root. But if we focus on the else part, here also if we see, we have popped 2 items. We popped root and we popped temp. So if root is the data that we want to print, that means previous item was not its right child. So what essentially we want to do, we want to put this temp back. So push of temp should happen onto the stack. Let's see this in our example. So once we took 4 out, 4 is popped. Previous item of 4 is not its right child. So we come to the else part, because pop of s says this is 4, root contains address of 4, temp contains address of 5 because that is second pop we are doing. Now we are checking if temp equals root right, that means is 5 equal to right child of 4, which is not true. Root is 4, 4's right, is that equal to address of 5? So here that condition is false. So what do? We come to the else part. In else part we simply print root's data. That means 4 has left and right child covered. So on output the first thing that we print is 4. After we are done that, we push 5 back. So 4 is removed and printed. 5 was also removed, previous pop removed that. So we push 5 back. So 5 comes here. Now after this, what is the next thing that should happen? After we are done with this, right now if you see, our root is pointing to, root was pop of s, which means root is containing the address of 4, which we have printed anyways. So if we go up in this loop, what will happen? Root is pointing to 4, which is not null, root's right, it will proceed from here. This is not null, it will check its right, which is not null, and it will push it again, which means we'll go into an infinite loop. If we proceed like this, we'll go in an infinite loop. So what essentially we want to do is, after this step, we really want next thing to happen is, next thing should be popped out of stack, because 4 is printed, that means we are done with it. So we should go to the parent of 4 and start the same procedure again. So what is the way we can force our program to pop the next item from stack is when root becomes null. So if we set root to null here, only then when it goes up, it will not enter the while loop, and we make sure like next thing that happens is we pop from the stack. So this is a very important condition to remember, otherwise our program will enter an infinite loop. Now this part we are done with. So last thing that we have to make sure is, when we come here, when we are doing a pop, we are not checking before pop whether stack is empty or not. So if we do a pop on an empty stack, what will happen? There will be a crash, because we have put assertion in our pop code. So let's put that condition. If is stack empty, if our stack is actually empty, that means we are done with our traversal. We don't even need to pop anything. Our stack becomes empty, means all the nodes have been printed onto the output. So that is first check that we have put. But if you really notice, we are doing a pop again. So chances are, if there was only one node in the stack, so we check for the condition, we pop that node and we come out. Now the stack becomes empty. So we are doing another pop which can happen on another empty stack. So we have to make sure, if after first pop operation stack has become empty, then essentially that is the last node that was there on the stack. So if is stack empty, then what, this is the last node, then what we can do is we can simply print the data of this node and we can break from here safely, because if stack has become empty after the last pop, that means this was the last node that was onto the stack. We just print the value of that, because it's left and right both are covered, so we can print the node and we can break. If this is not true, then we do another pop and then we do comparison. So with this, looks like our function is complete. Just one more check. If main calls post order traversal with root as null, so in that case we don't even need to create a stack, we don't need to even enter this loop. So in the beginning itself we can put a if check. If root is null, that means there is nothing to print. And as a convention, since we are putting one line order traversal, so we'll print this as an output, so that even if someone has passed a null route to us, we can display a blank line where post order traversal is written and there's nothing, no element printed after this. So that's pretty much our post order traversal. We have added a signature here, we have implemented our function. So let's add a call from main to post order traversal. So let's call and validate the code that we have written, whether that works fine or not. Oops, too few arguments. Okay, here we are calling destroy stack, which needs stack from us. So one error that we have made. Second is declared here. Okay, I think that's good. So yeah, it compiled. So now when we run it, we see post order traversal. 4 and 9 are printed. Then after that their root is printed 5. Then left tree is completely over. 1 does not have a right subtree, so next is 1. After 1 is printed, that means entire left subtree of 2 is printed. Now we have to move to the right of 2. Right of 2 is 3. So 3 is printed, and after that 2 is printed. So that is our post order traversal.